Okay, let us continue with chapter 5, nuclear physics. Okay, we split into two parts. The first part is about the nuclear model and the atomic. The nuclear model and atom. And the other part is just radioactivity. Okay, we split into two parts. So before we go into the first part, we need to understand what is an atom. So we need to go back to the history of scientists discovering a atom. Okay, so here is a model, a different model of atom. We start from the 1803. We have the solid sphere model from John Dalton. So that's not the important part. We just skip through. So we need to understand how we got from the plant pooling model, into the nuclear model. How we got from here to here, because as we know, currently most of the model, not most of the, currently we think the model is almost look like the nuclear model So it's very important to understand why we are start from pump pooling model to the nuclear model, and the planetary model is quite similar to the nuclear model and so on so on. So how we go from the pump pooling model to nuclear model. So the pump pooling model, we just understand that we only have the whole atom is a positive, and we have tiny bits of electron as negative. So the whole atom is positive. And the nuclear model is the middle part is the nucleus have a positive charge and surrounding it with the electron with the negative charge. So how do we go from this model to another model? How we got that? So to understand it, the Ernest Rutherford, they did an experiment to try to figure out something else. But in this experiment, they figure out there's is not what it looked like. So they starting to have this kind of idea on what is the actual the atom look like. So they call it a scattering experiment. So what they did is they try to bombard the alpha particle from one side towards the gold. So they try to bombard. So for example, here's a gun. Try to bombard to a gold over here. And what did they expect? What did they expect from the alpha particle when it hit the gold foil? Okay, so when they think that, or when alpha particle hit the gold foil, it should be reflect back because of the particle models. They think it's like this. So they think if once they emitted the alpha particle, they will reflect back like this. But when they started to do this experiment, they surround it with a detector over here, and they figure out like almost 80 to 90% of the atom passes through. 80 or 90% pass through. Some deflect over here, but 80 to 90% passes through. So they figure why it passes through, it should be reflect back. And they think in a way that it's actually the middle part is the alpha particle and surrounding it with electron little to no mass at all. Okay, so when the alpha particles hit the gold foils, most of it pass through because they only hit the electron and not the proton, not the nucleus, and they only reflect one inside. So they think that because of it, they come up with the model of this model, a nuclear model. Okay, so this is the reason why is it So they propose the model should be like this. Okay, so once we understand this part, we going further a bit, we need to understand what is the subatomic particle. So subatomic particle is like inside an atom. What's the particle look like? Okay, so subatomic particle split into three: a proton, a neutron, and a electron. So this part you need to understand So proton, neutron inside in the nucleus. So I say nucleus. and nucleus, and this not. And the charge is positive 1.6 times 10 to the power of negative 19. C is a charge, and the electron, it's a no, electron will be negative 1.6 times 10 to the negative 19 is per charge. Okay, per. Okay, if it's relative charge, it's just 1 positive and 0. The mass of it is 1 times 67. This one I think no need to memorize. Okay, 1 times 67 times 10 to the power negative 27, and this is 9.11 times 10 to the power negative 1. And what's the ratio is 1840, and this one is 1 1. The ratio lah, look like. Okay, so this the difference between them. And going forwards, we need to understand what's the difference between them and what the usage between them. So proton, we can say that proton is actually in an atom, a proton is to determine the type of element. So different proton number means if an atom has different number of proton, it's considered a different element. So it determines the element. As neutron, they don't determine the element, they just determine the isotopes. Okay, we later will discussing why they have different isotopes, but it usually means that if there's a different neutron number, means that there are different isotopes. Okay, and third is electron. They determine the charge. Okay, because proton is fixed, so if there are more electron than proton, means there's a negative charge. If more proton than electron, means it's a negative charge. It's a positive charge. So on and so forth. So we need to understand what is the usage of the subatomic particle and whatnot. Okay, going forward, we need to understand. Since we already understand what is inside an atom, the subatomic particle, something like that, we now need to learn about what is nuclear physics. Nuclear physics is important because we split in two, which is called a nuclear fission or a nuclear fusion. So a nuclear fusion process is just that the heavy atom nuclei and heavy atom will, like uranium, will split into two or more smaller nuclei, releasing large amount of energy. Okay, so you can see, for example, a uranium 235, or say 235. So this is a mass number. Okay, and below down is the proton number. So we say proton number, and this is the mass number, means the mass number is the number of proton plus the number of neutron. So proton plus neutron, we get the mass number, or we you call it the mass number. It's much easier. Okay, or we call it a nuclear number. So this is uranium 235. Okay, uranium 235. When they hit by a neutron, so it's 1 0 because there's not positive, so it's just 1. Okay, and it will split into two smaller atom, which for example is 141 and 56 barium, and the other one is 92 krypton and 36. And other than that, it's also split into three 310 neutron. Okay, so you can see that's a uranium 235, when then plus a hit by a neutron, and they split into a barium, a krypton, and 3 more neutron. And other than that, he also come out with energy. Okay, so usually human try to harness this energy to and convert into electricity. So we have the nuclear power plant because of it. Okay, so you can see in here, it says the process a neutron hit and large nucleus and split into two equal mass of nuclei, which is and 3 neutron and radiation energy lah. The neutron then is then hit with another neutron. So this will continue, hit another. For example, it will hit another new uranium and will continue splitting again. So this is a continuous process in order to harness all the energy. Okay, so this is the first part. Okay, this is the first part for a nuclear fusion, means splitting. Okay, nuclear fusion is opposite of it, is fused together. So we call it a nuclear fusion. For example, two light nuclei and combine to form a single more massive nucleus and release a tremendous amount of energy. So nuclear fusion actually give more energy than nuclear fusion. Okay, but we unable to do that yet stably. Okay, for example, is a sun. The sun actually do this process. Okay, for example, hydrogen 2 1 means one proton and one electron, and the other one also same. You call it the deuterium. We fuse together become a 3 2 helium, and neutron. Okay, and this is also when they fuse together, they also release energy. Okay, and this energy also can be harnessed to do something else. Okay, so also let's look example of a nuclear power plant, how we do it. Okay, how we harness those kind of energy and how we harness it. Okay, so for example here we can see there is a nuclear power plant over here. So a nuclear power plant over here, you can see the core here is actually there's a lot of uranium-235. Okay, so there's a lot of uranium-235 over here. Uranium-235 in the core there. Okay, so this also have control rod. Okay, so why do we need control rod? Later we will discuss it. Okay, so the uranium will release energy once they bombarded by the neutron. Okay, and they release energy. Then if the water pump is over here, you will heat up the water, and the water will come here. They'll come here, and you will heat up another water over here, and the water will be turning into steam, and your steam will turn the turbine and will generate electricity. Okay, so this is how we do it. We heat it up, and we heat another up, then we will turn the turbine, we generate electricity. The steam will then cool down and pump it back to the place. So we heat, cool down, heat, cool down, heat, cool down, heat, cool down, something like that. So okay, come back to the question, why do we need control rods? So the purpose of control rod is like this. If it doesn't control the nuclear fission process, we say 1 go to 3, 3 go to 9, 9 continues so forth, 27, 81, and so on and so forth. It's getting bigger and bigger, and you are actually causing an explosion. So because of that, we actually need to control it. For example, for one uranium, we only want to release one neutron, and the other two neutrons that been released, we can capture back. So it won't get bigger. The process, the nuclear fission process will get bigger. So the controller is actually uses when we say we sense a lot of neutron, we will send it down here, and the neutron will actually hit the control rod and will be absorbed by the control rod, so it won't hit another uranium. So this is how we control the process lah. So sometimes if too little of neutron, we will take the control rod up, so the process will begin. The nuclear fusion process will keep on increasing, and if it's too much, we just put the new control rod back inside. Okay, so how the whole process is going like this, nuclear power plant. Okay, let us continue. Okay, so this is actually the whole process of nuclear fission, all the process we already talked about, starting from we have the nuclear model of atom, and how we discover the Ernest Rutherford nuclear model, and what is the subatomic particle. In fact is before we figure out the nuclear model, we actually figure out the proton first, and later on we only discover neutron. We discover proton first before we discover neutron. So that's why over here we just like, inside there is just positive over there, and not the neutron. Okay, because later on we only discover neutron. That is why. Okay, so sometimes we think like, what is the purpose of using we hit neutron, we hit the proton? Okay, because because if it is positive, you can shoot it lah. If neutron, we not able to shoot it lah. So that is why we use proton of a particle lah, in a sense. Okay, let's continue the other part of radioactivity. So before radioactivity, okay, the energy released just now we discover from nuclear fission, all this process, we actually split into 3. Okay, we release the energy by split in 3 types, which is alpha particle, beta particle, and gamma ray. Because gamma is not actually a particle, it's just a wave of energy. Okay, so we need to understand what's the difference between them. Okay, so once they undergo radioactivity, once they undergo radioactivity, will really decrease. But you might be confusing how radioactivity. Okay. So before we go into the type of radiation, we need to we need to talk about how radiation occurs. How radiation occurs. So one of the way that radiation occurs is, for example, an element. For example, uranium. Okay, uranium. So uranium, we have a proton number. We have the proton number is 32, and the neutron number will be 235 minus 92. So we get the number. Can we get the number of this? 235 minus 92, and we get a number of 143. So you can see that the number of neutrons is actually exceed the number of proton. That makes the elements unstable. When there's too much neutron inside, it means that the center is too big already. We cannot hold the atom cannot hold the particle together closely. Okay, they cannot hold together. The atom cannot hold together closely. So that's why they need to emit energy, or emit the electron, or not electron, sorry, emit the proton or the neutron in order to become a more stable atom. So the center of an atom, they will release radiation to become stable. Okay, so because of that, there's 3 type of radiation they can emit. So alpha, beta, and gamma. So this is how we get it: alpha, beta, and gamma. So the release of this one. And we just now we talk about the isotopes. So if different isotopes, so if the isotopes number with high number of neutron, it actually means that it's unstable, and it will try to emit those radiation in order to go back to the stable states. Okay, so that's why isotopes is important in a sense of that. Okay, so what's the difference between alpha particle, beta particle, and gamma particle? So alpha particle is a helium. Okay, a natural characteristic of helium is not actually helium, just is a 4-2 helium. What do you mean by that? 4-2 helium. So alpha particle is called a 4-2 helium, means that they have 2 proton and 2 neutron and 0 electron. Okay, 0 electron. If there are 2 electron, means that it's not positive charge. Okay, so it's just 2 proton and 2 neutron released from the center. So that's why there's no electron release. Okay, it just released from the center, coming out from the center of 2 proton and 2 neutron. So it came out like this. Okay, and this is called an alpha particle. A beta particle is the release of a neutron. Right? But they say beta particle is an electron, high-speed electron. But why do we say release a neutron? So I say already, if we have a lot of number of neutrons, it's causing it to be unstable. So once we release a neutron, the neutron will turn into a proton and an electron. So how is it done? I don't know. Okay, it just says that when it release the neutron will turn into 1 proton and 1 electron. The proton will go back inside the nucleus. So the neutron come out, the proton go back inside the nucleus, and the electron emitted out as radiation. Okay, so neutron is when the beta particle, when neutron emitted and the proton go back inside and the electron come out. So we call it a beta radiation. Okay, so what do you mean by beta? Beta means is the negative charge electron. Okay, so the neutron turn into a proton and a electron. The proton go back and the electron come out. So we call it as a beta radiation. Okay, so the alpha radiation is emit of 2 proton and 2 neutron. The beta is emitted as a electron, electron come out, and gamma is just energy. It just come out as energy. Okay, so that's why it is doesn't have any proton, neutron, electron, doesn't have any. Okay, because it's no energy inside, then you just release out. Okay, so we need to understand electric characteristic in between helium, electron, and electromagnetic wave. The charge is positive, negative, and neutral. The electric field, because beta particle is in negative charge because of electron, it will go towards the positive side, and the helium is actually positive charge, so you go to the negative side. Okay, and gamma is just neutral, so you're going straight. So what we can understand, what's the difference between a beta and gamma, beta and alpha, if it doesn't say that it's a positive or a negative charge. So we know that beta is actually an electron, so it's very light compared to two proton and two neutron. So that's why it will just attract towards the positive side much faster than the alpha particle. So they say the journey is over here, and say it's going up over here already, and alpha particle is going down, much further down the road. Okay, what about magnetic field? The magnetic field, how is travel, how is affect the radiation. So NS over here, when positive, negative, and positive, negative, and a neutral over here. So gamma is neutral, so it doesn't change. So we already study about left hand rule. Left hand rule, which means that if there's a charge or there is a magnetic field, it will induce a action. So by using the left hand rule, you can understand that NS and the charge moving here, so the alpha moving up, also like that, and the beta is going that side. I think it's not left hand, it's right hand. Okay, right hand rule. Okay, is it right hand rule? Let me think. Right hand rule. Okay. Yeah, we're using right hand. It should be using left hand. It's a bit weird over here. No. Yeah, you're using left hand. Yeah, correct. We're using left hand. Okay. Yeah, using left hand. Yeah. Okay, my bad. Okay, using the left hand rule. I stayed over here. Left hand. Okay, because we already have the electron, means that we are not inducing electron, we are inducing motion. When you induce motion, we use left hand, means the motor. We induce the motion. Yeah, okay. So ionizing power, what do you mean by that? Ionizing power means that once the particles, okay, knock the alpha particle, beta particle, or the gamma, knock a neutral particle, once they knock, it will split the particle into ions, means positive charge and negative charge. Okay, so when the splitting of ions, we have splitting of ion means ionizing power lah. So if the alpha particle is quite heavy, so they can knock a lot of particle before it come to a stop. In bigger size, it can knock a lot of particles. So that's why we call it a high ionizing power, because it's quite big and it can knock a lot of particle. And beta particle is moderate because it's just an electron, gamma low because it's just an energy. Okay, penetrating power, because of its size, alpha is quite big, so it cannot penetrate. It's low in penetration power, beta is moderate, and gamma is high. You can see over here, a piece of paper can stop at alpha. For aluminium, beta can stop by an aluminium, gamma can stop by a tick of lead. So the range in air, several meters. So the main part we need to understand about these three is the ionizing power and the penetrating power, in order to explain why, what is the usage of this one, what is the usage of this one. So it can be used in our real life on these particles, this kind of stuff. Okay, let's go into the other part. So we already understand what's different type of radiation. We need to understand what's the use of them. What is the use of those particles? Before that, I'm going to see some of the radiation. Can see. Okay, so this one is just a proton and neutron. This is inverted, so it's not that good lah. But we can still take a look. So you can say is that 1 to 8 neutron and 83 of proton. Once they release, we'll minus 2 proton and minus 2 neutron, minus 2, it become 81 and 126, and it's 2 proton and 2 neutron. Okay, so it's very simple. For beta, it just for 15 proton, 17 neutron. So the neutron will minus 1 because as neutron come out, so it becomes 16. And the proton will be plus 1 back, so it becomes 16. Okay, so it's actually 32. So 32 Okay, this one is 32 and this one is 32, and it will be the same but different element because of the proton number, and release an electron. Okay, so the neutron is actually converted into one proton and one electron. So the proton go back and the electron come out. Okay, and gamma is now no change at all. Gamma is no change, 2733, 2733, no, just energy come out. Okay, when energy come out, it's much more stable, something like that. Because the energy is very excited, so the energy come out, it become more stable. Okay, so this is it. So what's the use of radiation? Okay, this one you can understand. So for example, if you have a technician 33, you can treat brain tumor, medical. Okay, gamma, usually gamma, sterilizing medical equipment, treatment. Okay, we all learn it, gamma ray from the electromagnetic wave from chapter 4. And industrial use, we can actually control thickness of metal for gamma. Beta can control thickness of paper or plastics, something like that. Okay, so gamma I think is a metal piece. And agriculture, okay, determine exhaustion of fuels of phosphate. This one usually we don't memorize. Radiation, this one also don't memorize. Okay, food preservation, gamma kill bacteria, food preservation. Okay, so something like that. Okay, so this some of the radiation you can memorize, you can don't memorize, is okay. You can just understand what is the use of that, and they will actually ask what's the difference between them or what's the use between them. You just need to understand like how is it used by using different ionizing power and penetrating power. Main three things in the usage I like to teach students is the first, for alpha, because of the ionizing power used for smoke detector. Okay, so if there's smoke over here, the alpha particle when it hit, it will ionize the particle, and it will become connected to the electric circuit, means that it will detect there's a smoke. Electric circuit means there's a pulse, have pulse. Okay, it have electrical signal. Okay, so because of it, the high ionizing power. For beta, we use a thickness. Okay, determine thickness of paper. And gamma usually determine underground sewage, we can say the leakage or hole of pipe underground, because gamma when thick leak pipe, the gamma cannot come out, but there's a hole, it can come out and it can detect over on top of here. So usually gamma usually used to detect the leakage of pipe. Okay, so basic usage of radiation. Okay, so what is half-life? Okay, half-life you can say is that because we don't know when the radiation occur, because I already say if the isotope is unstable, it will actually emitted out, the energy come out, or alpha particle, beta particle radiation come out. But we don't know when it will come out because it's quite randomized. So how we understand it and how we calculate it is because there's a pattern of it. So isotope have a half-life, they have a fixed half-life. For example, if the activity is 100% or 100, activity means the emit of radiation, is 100 activity means they emit 100 of radiation per hour, for example, per hour. By the time it go into 50 activity, it's usually take different element different time. Okay, maybe if this one usually 3 hours, the time it took to become 25 is also going to be 3 hours. It's fixed. The time of the activity become half for each element is fixed. Okay, the time for element goes into half of activity is fixed. If from 100 to 50 using 3 hours, from 50 to 25 use 3 hours. Sometimes for 100 to 50 maybe they use 3.5 years, and for 50 to 25 you're also going to 3.5 years. It's going to be fixed for different element See what is the element or what is the isotopes. Okay, so it's fixed. So half-life is mean by that. So half-life is the time taken for the number of nuclei to decay half of its original number. Is fixed. For example, this one you just say 1 hour to give from 100 to 50. So 50 to 25 another hour, 25 to 12.5 is another hour. So you go down like this until it's become, it won't be zero, but it's negligible lah, close to zero. Okay, so this is actually half-life. So half-life is very important. For example, this here is a question you can understand. So half-life, for example, when we try to detect an element with, for example, element X. Okay, the activity is 1000. Okay, the half-life is maybe 3 days. Okay, but when you say the detector detect, it's not only detect TECK TECT, yeah, detect it not only detects the radiation from X element, but it also detect the background radiation. For example, the background radiation is 50, so I just say 50 background radiation. So when I say the detector detect is 1050 activity, then it says after maybe how many days is better? 6 days. Okay, what's the activity? What is the how much it detect? How much it detect? So how we do it? So first thing first, we need to minus the background radiation. So 150 minus 50, so you get 1000, means the original number. And 3 days means 6 means twice lah. So 3 days is going to 500, and another 3 days go to 50. So the detector you will detect not only the background, not only the sources of X element, but also the background radiation of 50. So we need to plus back the 50 in order to get the detector number. So it's 300 activity. That's right. Okay, so this is how we do it. Okay, so we need to minus the background radiation and add back the radiation, the background radiation. Okay, so the background radiation doesn't change. Okay, well, what do you mean by background radiation? Background radiation means the radiation on the surrounding. For example, cosmic ray. Okay, cosmic ray, rocks. Some type of rocks also have food. Sometimes some food also have. Okay, so this is how usually background radiation occur. Okay, so there's somewhat background radiation in our life. Okay, so this is all of it. The last one is talk about the Geiger-Müller counter. Okay, it's quite similar to usage in alpha radiation. So Geiger-Müller counter is like this. This chamber, and this is a rod and a rod. And this one I put a like for example somewhat a battery over here lah. Somewhat battery and a detector to count rate like this. Okay, we using count rate, not activity lah, but it's okay. So this one here is for example positive negative. So this one positive negative is not connected, so the electron won't move. And this steel chamber with argon and xenon, so it's quite stable. Okay, so it won't connect, so no pulse, no detection. So for example, if ionizing radiation such as alpha background enters the tube in ionizing, guys produce a pair. So when you go inside, it will actually ionize, become electron pair, ion pair. So we have electron. So the electron, the free moving electron, generate ionized radiation, will accelerate by electron field and collide another gas, create more free chain reaction called electron avalanche. So starting in just a bit, but you will keep on continue collide, it become more electron. So if the electron avalanche leads to a significant number of free moving electron and a detectable electron pulse. So once there are a lot of ions, this positive will connect to the negative and it will detect a pulse. So it means more electron means more pulse, bigger pulse, means that there's a high penetrating, high ionizing power inside lah. So if there's a lot of alpha particles, it will be higher pulse, will mean higher detection, something like that. So we can count the tube, count the number of electron pulse, produce free time, the proportion, the intensity of radiation. Yep. So we count, you call it the count rate, we count there's how much radiation using this Geiger-Müller counter. So this all chapter 5, everything inside, how type radiation, use of radiation, how is it half-life, how is it detect, something like that, usage, something like that, and what is the nuclear physics, the model, the atom, fusion, okay, of it. So this is how is it. Okay, thanks.